F word and I said it now and you heard it.
Really?
Yeah.
I don't remember that.
10th grade.
Oh, it was me 10th grade too. Let's go.
Okay, let's do what we gotta do. We learned the lesson, play a game, and we can go home early.
Ikimashou.
Okay, so today we're gonna learn Green's theorem.
Green.
Oh,
This is a theorem to compute line integrals.
Raymond Green.
I saw it.
Oh, no, it's not Draymond Green. I forget the guy's first name, but it's not Draymond. Anyway, it's written right there. So to compute the work with a force field of P and Q, where P and Q are functions of X and Y, then all you have to do is this. Double integral over omega. Now what's the first one? Partial of Q with respect to X. See, this is another formula you want to put down on your sheet, yeah? Minus the partial of P with respect to Y, dx dy. I wouldn't even know how to start like trying to prove this, but in fact, sometimes the book says the proof of this is beyond the scope of this course, so, you know. So where the line integral is taken along C in the clockwise direction. Okay, I want to do one problem because there's something neat about it, that's why. I want to do a problem like 1C. So, oh, they put the integral in that form already. So, double integral over omega of, can somebody read it to me? Except I'm going to change the numbers.
3xy plus y squared.
Okay, so 4xy plus 3y squared dx plus
2xy plus.
So 3xy, just change the number a little
7x
bit,
squared.
plus 7x squared dy.
C dot dot. What is
They don't even put brackets around it. So interesting. Let's put brackets around it. Where the curve is a circle, okay, let's give it a different center. How about x minus 3 squared plus y plus 1 squared equal 4? Then how's that then?
Yes. Plus.
There's a plus in between?
Yes.
Oh yeah, right there. Okay, so if you look at Green's theorem, this is P, this is Q. Okay, so all you have to do is compute the partial with respect to Q. Okay, I mean partial of Q with respect to X. What's the partial of this with respect to X?
3y
3y
plus 14x.
14x
So rude.
minus, now what's the partial of this with respect to Y?
4x
4x
plus 6y.
plus 6y. Okay, and we're going to integrate that over omega. This is dy. Dx dy. Double integral over omega. Omega is this region right here. This is omega right there. Okay, now let's simplify this. What is 14x minus 4x?
10x.
10x. And then what is 3y minus 6y?
Minus 3y.
Minus 3y dx dy. And then we can separate this into two integrals, yeah?
Yes.
So where am I going to fit this in? Over here. So we got a double integral over omega of 10x dx minus the double integral over omega of 3y dy. What am I doing? This is dx dy. This is dx dy. And then of course, you can take the 10 and put it outside the integral. Same thing with this 3. And then you look at this, look at that. Hey, use some body.
Oh, that's the center.
Yeah, isn't that the thing we have to compute for the centroid?
Yes.
And for those of you who forgot, to compute the x-coordinate of the centroid, don't you do a double integral over omega x dx dy over the area of omega?
Oh, wow.
And then same thing with the y bar. To compute that, you do the double integral of omega of y dx dy all over the area of omega. Correct?
Neat.
Yeah, that's right. There's something neat about this.
Yes, sir. Neat.
Okay, so how do I compute this then? This is what we want to compute.
Yes.
So if you multiply it, so this will simply be the x-coordinate of the centroid times the area of omega. This doesn't happen all the time, but once in a while it comes out to that. And then minus 3, and then this thing over here is the y-coordinate of the centroid times the area of omega. Okay, well, this is a circle, center at 3, -1, boop, 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 boop. Radius 2. So what is the centroid? Isn't the centroid simply the center of the circle then? Which is 3, -1. So this is x bar, and that's y bar. So we got 10, x bar we know is 3, and what is the area of omega, which is a circle of radius 2? 4 pi, right? Minus 3 times y bar, which is -1, times the area of omega, 4 pi. And so what do we get? 120 pi plus 12 pi. Final answer, 132 pi. But then, see, you can only do that if there's like an x or and a y there, yeah?
How do you do that without that?
No, you just solve it.
Then you gotta do this integral then.
How do you get the integral value? Do you do the circle thingy?
Oh, you mean if we had to compute it over here?
Yeah, is that the same thing as we did?
Oh, yeah, oh, who even writes it like that? Okay, so first, if I were me, I would integrate with respect to y, then with respect to x, right? I thought we did this last
And then the
chapter.
equation thingy and then the.
Yeah, so what you gotta do is you gotta solve for y in this equation, yeah? Yeah, let's just do it for funsies. Too late if I'm doing it. Y plus 1 squared equal 4 minus x minus 3 squared. Y plus 1 is equal to plus or minus the square root of 4 minus x minus 3 squared. So y equal -1 plus or minus the square root of 4 minus. See how messy this is gonna get? So the limits for y is gonna go from -1 minus the square root of 4 minus x minus 3 squared to -1 plus the square root of 4 minus x minus 3 squared. And then when you integrate with respect to x, it's gonna go from here to here. So what is that, 1 to 5? Isn't that a lot easier?
Yeah.
Because that's gonna be a terrible integral. Yeah, that's why Green's theorem is good. And that's why we studied centroids, we can actually use that here now. Now, not all the problems come out to where you can use the centroid, but if you can, it makes life a lot easier. So pretty easy, yeah? All right. Oh my goodness, look at the time. We are done. Let's play a game and we're going home early. What game did we play yesterday?
No,
The
mathematician.
scientist and mathematician.
It's a part.
Yeah.
I took 30 minutes to get the center of a hemisphere. Is that?
I didn't even
the
get
extra
it.
one is yours.
I didn't
You mean the 3, 8,
No,
3, 8?